and I'm going to walk you guys through how to make a PCB once you have a design in front of you. Now this is more relevant to electronics and telecommunication, computers and IT, but it's not necessarily limited only to those branches. Other branches can also, other students from other branches can also benefit from this, because this is a sort of a mechanical kind of a thing. It's a CAD, basically CAD tool, which we are going to discuss. Now, but before that, we must know some basics or primitives of the PCB process and the PCB itself. So let me dive into the PCB directly with a very short presentation of the PCB primer, I call it. So we start always with what is a PCB and what is PCB made up of. So we can see here that the basic PCB is made up of a copper clad fiberglass material, and it is basically composed of what is called as a substrate, and we have what is called as a copper cladding, which is nothing but two copper plates which are actually this FR4 of substrate is sandwiched between those copper claddings. Now this core material is very important because the core material is a rigid sheet of fiberglass resin and basically forms the basis or the background or the backbone of the entire PCB. All right. Then the next part that is important is the copper plating or the copper cladding as it is called. And this copper cladding comes in various different thickness sizes, and these are measured in terms of ounce, half ounce, 1 ounce, 2 ounce, 3 ounce, which actually translates to the thickness of in millimeters. It translates to the thickness of 0.017 mm and so on and so forth. So higher the ounce, higher will be thicker will be the core material, thicker will be the copper cladding. Now this has to be judiciously selected, because if I want to make a circuit which has to pass a lot of current, in that case a thin kind of copper cladding will naturally increase the resistance, and all of you know the amount of current flowing through that will influence whatever is the power dissipation across the copper cladding, as well as it will increase the heat also. So you have to be judicious as far as selection of the copper cladding is concerned. Most of the times 1 or 2 ounce board is more than sufficient. This is what you have to first of all tell your supplier. I'm just going to skim through this because so many things are cannot be covered in a short duration of time. My aim today, agenda will be that I'm going to divide this workshop into two different 2 days. Basically, the first day we are going to look at how to capture the schematic, that is how to transfer your design into the CAD tool, and then tomorrow we will go on with the PCB, actual PCB. Okay, so this is what I was talking about, the copper foil or the copper cladding, and it comes in various different thickness sizes. Okay, so then you have what is called as a solder flow, which is there on the top of the copper cladding. This is of course after the PCB is fabricated. Then you have what is called as a solder mask. Most of the times you see a green board, okay, a greenish tinge is there on the finished PCB. Now that actually is what is called as a solder mask, and that is what makes the what protects your components from the external world. Then the most important primitives which I was talking about, that is what do you mean by primitives? Primitives are nothing but the basic building blocks of the components of any PCB. When we say primitives, the components, it is better to understand the nature of these components before we start building the entire PCB. So the very first thing that comes is in the list is the trace, which is also called as the track. Now the trace is actually akin to a wire. Okay, it is what it is used to make the connection between 2 points. Okay, and the thickness of this trace, the width of this trace, thickness is decided by the copper clad, but the width, that is called as the trace width or the track width, is decided by the designer. Okay, the rule of thumb is that if I want to pass 1 ampere current through that particular connection, in that case I'm supposed to have about 1 millimeter width of the track. This is just a thumb rule. Of course, you can have a detailed analysis and detailed calculation for the thickness using this formula, but I'm not going to go into all those details. We have some ready reckoners also like this, that minimum conductor widths for PCB. You have a ready reckoner here. You also have a nomograph of some sort which says how much should be the track width corresponding to the current amount of current that is supposed to flow in that track. Okay, another important thing is the distance between the tracks. Now this is again a very important thing because most of the times we are dealing with DC values, and whenever we say DC voltage, and when two points are separated by a voltage differential, in that case if the voltage differential is high, or if the distance between the 2 points is less, then there is something called as ionization of the air between these 2 points. Sorry. And this is actually the cause of arcing, what is called as arcing. Now, in order to prevent this, we are supposed to have some minimum clearance, minimum distance between two entities. It may be distance, it may be the clearance, it may be the distance between a track and a track and a pad. We are going to see what is a pad, and a track or a via, and so on and so forth. So there has to be a minimum difference. Now this particular table suggests that for a 50 volt differential, you can have, let us say, 0.85 millimeters for uncoated PCB. Uncoated means we don't have the solder mask over there. Okay, in case of coated, it is with the solder mask. So whenever we are having, most of the times we don't generally go for coatings. So it is better if we stick to this figure of 1 millimeter. So there has to be a difference of 1 millimeter, distance of 1 millimeter between two primitives. Then one of the most important primitives in the PCB is a pad. Now a pad may consist of several different shapes and styles. Basically, what is a pad? It is a physical, let us say, a mechanical structure which is used for inserting the leads of the components. Okay, so there are two basic types of the pads. One is called as, this is basically the structure of the pad. As you can see, if you're talking about a pad, this is the component lead, and it goes all the way through the pad, and you have to solder it on the other side of the pad. It depends on what type of pad it is. So there are two different types of pads. One is called as a plated hole pad. It is also called as a PTH, plated through hole. The basic difference you can see here is that the upper layer and the lower layer are connected by a conductive plating over here. Okay, so you have to basically it forms a connection between the top layer and the bottom layer as well. If you see carefully the non-plated through, the difference is that there is no connection. Sorry, there is no connection between electrical connection between the upper pad and the lower pad. And basically, this is where most of the projects will fail if you don't consider using the plated through hole pad. The problem with this non-plated through hole pad is that it's quite possible that you may not solder both the pads to the lead, to the component lead. In that case, it so happens that there is virtually no connection between the upper layer and the lower layer. Specifically, when you are using a double-sided board, it is quite possible that there may be some kind of a connector track going from the lower end, and actually this pad just a moment, please. Am I audible? Hello? Hello?
Yes, sir, you are audible.
Yeah, I'll be keeping on asking this question because you never know when the connection drops out. Okay, so fine. Let us continue. So this is the basic difference between the plated through hole and the non-plated through. So display again for your understanding. You can see here what is the difference. Okay. Then we have the process of fabrication. Once you are through with the PCB design, the artwork design, then we start with what is called as the fabrication. Now there are various steps in that. I'm just going to skim through that. So we have the setup where the image is set up, and then we are going for the imaging. So you have two different ways in which you can transfer the pattern of PCB from your photo print to the PCB itself. We have direct imaging, we have indirect imaging, two different ways. And then we have what is called as the etching, where it removes the excess copper which is not there in the which is not supposed to be there in the PCB. This actually leaves what is called as the trace of the circuit, that is the artwork on the PCB. This is the concept of etching. So you remove the exposed copper and then you apply the etching component, and then you get the pattern which is transferred onto the board. There are other different ways like chemical etching process. Specifically, when you go for mass production of the PCB, chemical etching is more suitable. Now there are a couple of errors which happen during etching. Now basically, what is etching is removing copper which is there, which we don't want. Now here, for example, there are two tracks. It's a cross section of two tracks, and if the etching is not proper, as you can see, you will not have a separation of these two tracks which are lying there side to side, side by side. Okay, so if the etching is not proper, in that case, there may be a short between these two pads, these two tracks basically. And so what you have to do is you have to make sure that such a kind of thing doesn't happen, or in simple plain words, keep the tracks as apart as possible. That is the best deal. Okay, I'm not going to go into this. Okay, drilling. Drilling is nothing but once you make the PCB, once you go for etching and all that, then you are supposed to drill the holes for Hello, am I audible? Hello?
Yes, sir, you are.
Okay, there was a call drop, I guess. Well, anyways, so we go for such a kind of plating through hole and all those kind of things. Masking is there. As I said, masking is the last layer which provides protection to the devices. Okay, this is how it will look like. And finally, the board finish. Yeah. So I know this was a very who didn't have any background about PCB. I started with the PCB primer. Anyway, these are some general guidelines that you have to keep in mind while designing the PCB. Keep the track length short and wide. Use decoupling capacitors on each IC supply connection. This is very important. Keep the track short and sufficiently spaced from other tracks. List the physical dimensions of the components. We are going to see all these things and list the pin numbers. Now these are some Altium Designer specific guidelines. Now what we are talking about is Altium Designer here. I'm going to introduce what is the PDA tool which is called as Altium Designer, which is very famous in the industry. And of course it is not free, but then we can always try the trial version and get our PCB, practice with the PCB design. So the dimensions, basically, most of the times it is called it is basically addressed in terms of mils. What is a mil? Mil is a 1,000th of an inch, okay, which translates to 2.54 centimeters. 10 mils correspond to 0.254 millimeters, and 1 millimeter is nearly equal to 40 mils, 39 mils to be precise. Okay, then use visible grid and snap grid. Do not change too many of the default settings. This is one very important instruction which I normally pass on to my students, saying that if a small error is there in the default settings, unless and until you know what you're doing, don't do it. Otherwise, you'll land up with a wrong PCB, or maybe a PCB which cannot be routed at all. Defining the board dimensions. place the components from the top view, keep the components close together. So these are all specific guidelines. Interested students, participants can write this down. Then these are the recommended minimum pad sizes. You have 1.6 millimeters for via. What basically is a via? Via is it's like a pad, but it's not a pad. The function of a via or via, whatever you would like to pronounce it as, is to have a connection between the top layer and the bottom layer. Okay, if you're using a double layer PCB. So it's just a connector of some sort. Then for resistors, capacitors, you have 1.8 millimeters with a drill size of 0.8 millimeters. Okay. Then if it is a rounded rectangle, then you have 1.6 millimeters by 2.5 millimeters. This is for the IC pins and the drill size being 0.6 millimeters. Always use large pad sizes, okay? Because as I said, when the fabricator drills the holes, in that case, some copper is removed, obviously, and the remaining copper annular ring which is left over there may be insufficient for you to solder. And even if you try to solder it, it may come off, which is a very bad thing to happen. So the recommended minimum track sizes are 0.5 millimeters for the signal track and 2.5, 1 millimeter to 2.5 millimeter, depending on whatever is the current draw from that particular track. These are some certain component packages. Now, when it comes to PCB design, you have to be very much careful about the component packages. Unless and until you know what is a package, you will not be able to use the component, or rather design a PCB for that using that component. So components are available in variety of mechanical assemblies called as packages. Inside one package, there can be one or more parts. If it is only one part, we call it as homogeneous package. If there are different types of parts, we call it as a heterogeneous package. For example, here in this case, you have on this side you have a NAND gate over here. So all these components are NAND gates inside the PC, inside the package. So this is a homogeneous package. Whereas in this lower example, which is a relay, which is packaged into a relay, in that case, it is a heterogeneous package because it is consisting of different types of components inside. Then the most important part is again a footprint. What is a footprint? It basically is a projection of the physical shape of that particular package of the component, which will appear on the PCB. So it is very important for us to correctly select the footprint. Otherwise, you may land up with insufficient space to mount the component. So you can see here this kind of hat-like structure is a package mostly used by power transistors and the MOSFETs, power MOSFETs also. And the footprint looks like this, as you can see on the right-hand side of the slide. The lower one is the relay footprint, as you can see here, corresponding to the package that we have. So it is very important for you to select the correct footprint. The common package types and footprints are shown over here. Specifically we start with the passive components. Resistors are also available in different sizes and shapes, depending on their ratings. So you have something like this as a footprint. So this particular figure, which is shown over here, which looks like a yellow rectangle, which has protruding segments. So that is basically the footprint of a resistor. For variable resistor, you have a different footprint. Please remember these things carefully. So for package. Hello, am I audible? Hello?
Yes, sir.
Yeah, seems to have been a drop again. Okay, so continuing with this footprints, we have different footprints corresponding to different components and different packages. These are the common footprints for a transformer. These are common footprints for diodes. Diodes are also available in various different sizes and shapes, as you can see here. Now this is called as a TO220 package for this diode. Basically, these diodes are high current and high power kind of diodes. Okay, these are very small signal diodes. Small signal diodes they are called as, and you can see the sizes of the footprints will differ. These are the common footprints for LED. LEDs, again, we have different types of LEDs. Now, my focus here is to tell you about only the through-hole components. There are two types of components. One is called as a through-hole component, other is called as a surface mount device. So we will be discussing only on the through-hole components in this workshop. For the transistors, we have again different footprints, as you can see here. For ICs, again, it depends on the number of pins. So it's classified according to the package. DIP 40 means 40 pin package, DIP 28 means 28 pin package, 14 and 8 and so on and so forth. So basically, once you start making a PCB, you have to make sure that you are connecting it somehow to the external world. And for that, we require a lot of connectors. Again, different connectors will have different footprints. Now, it's not only that you are stuck with only the footprints given by that particular software. You can design your own footprint also. Most of the times, the mechanical design or the mechanical dimensions are given in the data sheet. So just by referring to the data sheet, you can create your own footprint. Now, in this case, I have created one footprint here for one relay which was there, which I have used in one of my projects, and its footprint was not available at all readily. So I created my own footprint, and you can use that footprint for your devices. It's very, very easy. Tomorrow, in the tomorrow session, we'll see the footprint creation also. Okay, some important things related to the ground. Because ultimately the current that is drawn from the power supply has to return back to the supply. Okay, and that is where everything starts getting different in the real world. So these are the various return paths, as you can see, and different, let us say these are the representations of different circuits. So how can you make the return path? You have to create the return path first of all. So how do you create it? So you can create it via the chassis itself. Okay, the chassis also forms as the return path. Now, in most of the automotive cases, if you see, the body of the car itself acts as the return path. So it is a chassis return. It is called as a chassis return. You can have earth return also like this. Okay, there are two different types of grounding. One is called as a single point grounding, other is called as a bus bar type of grounding. As you can see, the difference is very clear. Physically, this makes a lot of difference. Electrically, it is one and the same. Okay, why physically it will make a difference? The reason is going to be very obvious now in this particular example. So if your current return path is not selected properly, in that case, you may land up in trouble. Now, in the very first topmost figure, as you can see, I'm having a DC power supply of 5 volts and I'm supposed to drive a motor. That's fine. The motor is also rated at 5 volts. It may draw some current. Let us say it draws 1 ampere of current. And the trace or the track, okay, which is connecting the positive of the power supply to the motor terminal, it has got a resistance of 1 ohm. Please remember that these are copper conductors, and so they are expected to have resistance. It is not going to be a zero resistance path. Similarly, on the return path also we have 1 ohm. So as you can see, when I draw 1 ampere of current from this power supply, this 1 ohm into 1 ampere creates a drop of 1 volt. Similarly, here there is a drop of 1 volts in the return path also. So the net voltage across the motor is going to be only 3 volts. You are expecting it to be 5 volts. Now this won't be a problem for a device like motor, but especially if you're connecting a TTL logic circuit, okay, in this particular way, in that case it will fail because TTL expects 5 volts at its terminal. Okay, so what is the solution? The solution is to have a separate path like this, the lowest figure over here for the TTL logic circuit. Now you'll ask me, isn't the path length more and won't there be any more increase in the resistance here? The answer lies in how much current is drawn by this TTL logic. It will be hardly in milliamperes. So even if the resistance of this path is more, the drop across this will be very, very, very small, which even cannot, which can be taken care of by the noise margins of the voltage levels. Okay, so you don't have to bother about these things. So this is what is actually expected when you actually design a PCB. Okay, so this is the Altium Designer PCB design flow. You all start with the schematic entry, insert your circuit diagram and start with the schematic entry using the components and the footprint. Go for what is called as the electrical rule check, ERC. If there are any errors present, go back and correct your schematic. Then you go for what is called as a netlist generation. So what is a netlist? Netlist is a textual representation of the circuit, which is readable by a computer. Okay, and then you go for what is called as updating the PCB or creating the PCB. We'll see about this part in tomorrow's session. This part, the schematic entry and the use of the software for the schematic entry, is today's focus. So updating PCB is translating this netlist into the footprints and the connections. Then there may be some kind of errors present. We are going to see what is a macro error later on. Define the board edge, place the component, set the design rules, go for the auto routing. Now the most difficult part, that is the routing of the PCB, is done by the software. So you don't have to bother about routing it yourself. Of course, there will be some aesthetic changes that you can do later on. Go for what is called as a design rule check. If the errors are present, again route the board. Then said there is something called as polygon pouring, and the final artwork will be ready. So we are going to go through all this process in this particular workshop spanning 2 days. So now let me switch to the circuit diagram itself first. So yeah, this is not a circuit diagram which I intend to do today. So I'll just be switching over to circuit diagram. Which, let us say you have already designed this particular circuit, you have simulated it, and now you want to go for the PCB. Just a moment, please. Okay, are you able to see this PCB, this circuit diagram, guys?
Yes, sir, it's visible.
Yeah. So this actually is a different software. I just want to make one point here that once you create your own circuit diagram, okay, and simulate it, my job is now to use Altium Designer to make a PCB for this particular diagram, for this particular circuit. Now, what are the components? As you can see here, the components are an LCD. So we have an alphanumeric LCD, which is specified as 20 columns by 2 rows. Then you have your famous Arduino Nano development board. You have an RTC chip DS1307 along with a crystal of its own and a temperature sensor DS18B20. These work on different protocols. Let us not go into those details of the design of the circuit itself, because the focus is only for the artwork design or the PCB layout design. Okay, but just for fun, let us see whether it works or not. Okay, so my intention is to just measure the temperature and display the time. So as you can see, it is displaying the temperature. I'm simulating the effect of the temperature. I can increase or decrease the temperature here like this and see the effect over here. Okay, so this is what we are supposed to do. This particular components, this black rectangle which is encompassed by this border, this is basically only a virtual terminal which is not going to be a component. Okay, so the components in our circuit are only this DS18B20 temperature sensor, this resistor, then we are going to have the LCD, then we are going to have the main component, that is your microcontroller, which is there on the Arduino Nano development board. We are going to have two pull-up resistors for the SCL and SDA lines. This DS1307 is a RTC, it's a timekeeping chip, and a crystal. Crystal, as you can see, the crystal frequency is 32.768 kilohertz. Okay, so once you are sure that your circuit is at least working in simulation, the next step is to go for the circuit, the PCB design. Okay, so let me shift over to Altium Designer now. Okay, so are you able to see the screen for Altium Designer?
Yes,
Guys?
sir, it's visible. Yes, sir, it's visible.
So let us have a look at what exactly is this software. So this software is Altium Designer. The version is a little bit outdated, but then it's okay. Once you understand the concept, the design flow, you'll be in a position to adapt to newer versions. Okay, so this is called as Altium Designer software. It's an EDA tool. And okay, so this is the blank screen that we have. When we start with the project, just make sure that you follow these steps. Just a moment, please. All right. Okay. So we'll start with a new project. So file, start with file, new project. So you'll be presented with this particular screen. Don't change anything here. We are going to go for a default template. So you have PCB project. Now you can create your own PCB project folder, but let us not go into that. I'll just name it to be, let us say, workshop, and I'm going to locate it somewhere. I think is the okay. Let me share the screen, the desktop itself, so that you'll be able to understand what I'm doing exactly. Okay. So what do you see now, right now? I want this feedback because otherwise we'll be all working in blind. What do you see right now?
Sir, your Microsoft Teams screen.
Sorry?
Sir, the Teams screen.
Okay. You're not able to see the desktop?
Mm,
Check out, please. Are you able to see this new project window?
Yes, sir. It's visible now.
Okay.
Yes, sir.
Okay. So this is the project piece, a new project window which is presented to us. Now I'll browse the location to some. Let us say I start with a new folder. Okay. So the folder name is also workshop and the project name is also workshop. Okay. Fine. Or let us say the project name is RTC underscore temperature. So both something like that. So that makes some sense. Okay. So now we are presented with a an empty project. You see that empty project RTC underscore temp.prj PCB. Yes.
Yes, sir.
Okay. So since there are no documents right now, we are going to add a document for the schematic. Today we are going to focus only on the schematic capture. So file, go into file menu, select new schematic. So you'll be immediately presented with a schematic, a blank schematic sheet. Now let us first of all understand this schematic sheet properly. So you can see that it is divided into grids. These are the visible grids. The grids are also, the coordinates are also given over here on the lower left hand corner. Okay. The grid size is 10. Okay. There are no units here in this particular version. Okay. The important things that you see are this one. So this is called as a title block. That is where you make all the documentation, the name of the PCB and so on and so forth. So in order to do that, what we'll suppose do is place, go into place and click on text string. So once you select that particular text string, your cursor will change to a crosshair, and then now you can place it over here like this. Okay, right click to get out of the mode. Right click of the mouse button to get out of the mode. Now here you can double click on that text and write whatever you want. Now our project name is RTC underscore 10. So I'll write it like that only. And I can change the font size also. So if I want it to be a little bit bigger, I can do that like this. Okay, fine. So this is where you put all the documentation. There will be a number, revision, drawn by, sheet number, so on and so forth. So this is all concerned with the documentation part. Let us go to the entire screen and see that there are certain markings on the in the vertical direction and also in the horizontal direction. What are these markings for? As you can see, these are A, B, C, D on the vertical in the vertical direction. 1, 2, 3, 4 in the horizontal direction. So these actually break up the sheet into different drawing zones. For example, this drawing zone from here, this particular section will be called as A1. This will be called as A2. This will be called as A3 and so on and so forth. Okay, so it actually corresponds to something like a latitude and the longitude on a map. So why is this required? Because many times there are multiple components, n number of components. Let us say 100 registers are there, and you are supposed to locate one particular register. It becomes very difficult for a person who has not drawn that schematic, or maybe for some other reasons. If he wants to locate that particular PCB, if he doesn't have the location of that component, I'm sorry, of that component, he will not be able to. It will be able to waste a lot of time in searching for the component. So in that case, it is a best practice. So as soon as you uh, draw a component, place a component in this particular zone, make an entry as to which zone that particular register, that particular component belongs to. So that is the reason why we have these drawing zones. Okay. Now you can just use the scroll button of the mouse and the control key on your keyboard to zoom in and out. Okay. Right click, keep the mouse right click, right button clicked or pressed, and just you can pan through the sheet. Okay. All right. So with these basic things, let us see what we can do about this circuit. So we are supposed to draw this circuit on the schematic. Now, is that circuit visible to all of you right now?
Yes, sir.
So now you are looking at the circuit diagram itself. Okay. So let us try to create this circuit with us over here. So the very first component that you have to place is the power connector. That is how I basically start. So in a circuit like this, when you draw the circuit, if you simulate it, there is no power entry point or exit point. Okay. So in a PCB, in a real PCB, you are supposed to have a kind of power point over there. Okay, or power entry point. Now, as you can see, on the right hand side, there are a few tabs, and clicking on the tabs will bring out one of them is called as the libraries. So these are the built-in libraries. You will get two libraries by default: miscellaneous devices and miscellaneous connectors. Okay, these two are added by me so as to simplify the process right now. But maybe you may not be. You have to start with these basic libraries. Okay, so we'll start with the basic library. So once you click that library, you'll see all the components inside that library are listed in this window. Okay, so these are all connectors. Now we are interested in a power connector, so maybe you can select one from here, which is a header. So we require two pins, 2-pin connector. So maybe you can place it here like this. Okay. So see, I have not yet finalized the placement. Now by pressing the space bar, you can change the orientation. Okay. So once I am through with this orientation, I'll simply click it, right click to get out of the mode. Let us see the various things over here. The very first and most important thing in a placed component is its designator. This P question mark is called as its designator. So double click on that and simply type in power. This is where I'm going to supply the power. This header is not necessary, so you can hide this, the type of that connector. Pin number 1 and pin number 2. So these are the two pins. Now if you see very closely, are you able to see this? There are a couple of dots here and on the ends of the pins. See that? Guys?
Yes, sir.
Okay, so these are the valid electrical points or valid electrical connections. Okay, so we'll see more about this when we actually make the component. We can also create our own component, not necessarily limited to the libraries. Okay, so this is where we will apply the power. Now what I will do is I will click on this VCC net and connect it here. I'll click on this. Now I'm supposed to connect it. So this is actually connected. You can see here. Now if I want to make a connection, I can just pull out the wire, place wire, and start making a connection like this. Right click to get out of the mode again. So this is where my power entry point will be. Let us save this properly first of all. So I'm saving it as the main board in the project. Okay, so we are through with this first component now. Now let us start with the other components. So going back here, we have to place this LCD, we have to place this device, the board itself, DS1307, and so on and so forth. So we start with, let us say, these 2 or 3 resistors here. So go into the libraries, click on miscellaneous devices. Here I can scroll all the way down to locate this RES1. As you can see, the footprint is also visible here. You can place the resistor here. So we require how many resistors? 3 resistors we require. So I'll just place it here randomly right now. But make sure that as soon as you place a component, make sure to change the designator. Otherwise, there will be a duplicate connection. Here you can see there is a wiggly line, which is actually the error, which is shown by the software itself. It simply means that you have a duplicate part designator. R question mark is same here. So if I change this to R2, then that line will go away. This is R3. All right. Is that fine up to this point? Are you able to see the screen? Hello?
Yes, sir. The screen is visible.
Okay, fine. So now we are supposed to have a component called as Arduino Nano. Now, all of you know what is Arduino Nano? Development board. If you don't, let me just go to browser. You can see here. This is normally the board, development board. Are you able to see the screen?
Yes, sir.
So this is one what we have. This is the standard board, Arduino Nano board, which has got ATmega 328P as the main controller, that is a microcontroller, and some peripheral devices for you to connect between the serial communication and the USB. So it's a board which is used for development purposes. Now, not only that, because of this particular footprint of this board, you can directly embed it as a device itself. That is what I have done here. Okay, let us go back to. Okay, so we have to make a symbol. We have to make a component in schematic and then use it. For that, I may have to create my own schematic symbol. Let us see that. So I will start file new schematic library. So library schematic. So here I'm going to store all the schematics which I draw. You can see immediately the screen changes to a different configuration. Okay, there is a line over here like this, a coordinate system, as you may call it as, and then a new component by default is shown over here. If I double click on that, so here I will say I want to create a nano board, nano 1, because I may have some, okay, nano, doesn't matter. Okay. Should be here. Just a moment, please. So why it is not getting updated right now? Let us say in the description component reference here. Now it is proper. Now I've been using latest version, so there are some changes over there. Anyways, so so now we are supposed to create the symbol, schematic symbol. So how do you start? You start with a rectangle. Place a rectangle here, like this. Now you can stretch the rectangle later on whenever you want. Okay, by clicking on the rectangle and just pulling it using the handles, the graphic handles. Okay, Fine. So this becomes the symbol body. Now we are supposed to place the pins. For that, you can again go into this menu, click on pins. Now here it may start with something, some random number or maybe some other number which you have already used earlier. So in my case, it started with 7. In your case, it may start with 0. So in order to change that, I simply have to press on the tab button on your keyboard and simply start with like this. So designator 1 1. I'll place the pin. Now you can see here. Are you able to see this? That there is a difference here. How to place the pin? What should be the orientation? Now you see a cross at the end of the pin. Do you see a cross? Cursor is all right, but there is again a cross over there on the other end of the pin. Do you see that?
Yes, sir.
Okay, so that actually is the electrical connection. So if you place it like this, it will be wrong. It should not be placed like this, but it should be rotated 180 degrees. Now that you can very easily do that with the shortcut key X on your keyboard. Okay, or you can either even use the space bar for changing those orientations. Now this is proper. Okay, so now you keep on placing the pins like this. This is how you create. Okay, I'm not. Okay, let's create it completely. It is going to be a 15 pin device. Again, change of orientation and start placing here. So we have our, you can just stretch this like this. Okay. Now you can either select all the pins like this and shift them if I want to make the size of this rectangle bigger. So this is my schematic symbol. I have to save the library also, save my symbols. That is the name of the library. The contents of the library, number one component is nano. Okay, now I'm supposed to, so look here, this is what I'm supposed to replicate. So pin number 1 is D1/TX. So I'm supposed to provide the display name D, what was it? D1/TX. D1/TX. Similarly, I can go on adding all this. This is D0/RX. Reset ground. Right. Then D2 through D12. This is D2, D3, D4, D5, D6, D7, D8, D9, D12, Okay. So there has to be 15 pins. Let me see what happened. Yeah, 10, D11, and D12. Complete one side, but some pins are multi function pins. For example, D11 is MOSI, master out, slave in. So I'll mark it like that. All right. Now the other side, this is SCK/D13. I'm just going to omit that LED. It is the internal LED which they have provided on board LED. 3.3 volts ARF. This is the analog reference used for the ADC. A0 through A7. Okay. Then we have plus 5 volt reset ground V. Okay, this is what is the new symbol that we have created. Just don't forget to save it. All right. Now if I go back to my main schematic, click on the libraries, and I can add this particular library which I have created, or it is, since you are talking about the same project here, it automatically gets added over here like this. So there are various ways in which you can do it. Libraries, you can install the library. If it is external to the project, if it is internal to the project, it becomes visible immediately. So you can see here that my nano is now visible here, and simply say place nano, and now I can start drawing the circuit diagram around it. So I'll call this as U1. Designator is U1, and my symbol is now ready to be used. All right. Now many times the symbols are also readily available. So one of the things which I'm going to show you is the symbol for the DS1307. So for that you can go, let me just go to the browser, click on Snap, go to the location Snap EDA. Snap EDA is a website which gives you all the footprints for various different softwares. So I just have to type in DS1307 I get a list of all the available footprints. So you can see we are interested in DIP, not in the surface mount package. So I just click on this BS1307, and you can see that the packages, the symbol and the footprint will soon be available here. Okay, so once you do that, you can download it. Of course, you have to create your own login, which is a free sign up. So you can just log in. It will ask me for which format. Of course, it will ask me for login. Okay, now I have logged in, and now I can download the symbol for Altium Designer. You can see that the library is getting downloaded. Once this library is downloaded, you can just go into the paste it into your whatever target directory. Here in my case, it is presentation, Altium training, and workshop. So here I will simply copy it to my project directory. Once I complete that part, what I can do is I can install that library from here itself. So from install from file. So let me go back to my directory there. Here you can see DS1307 is being recognized as a legitimate library. I can open it and then it gets installed. You can see here that the library has now been installed over here. Now it comes with its own footprint, so you don't have to bother about creating the schematic symbol or the footprint also. Unless and until it is a specialized components, most of the components, we have a library for that on Snap EDA. So I can place it. I'll place it here. Call it as U2. It has to be connected to VCC and ground. Similar is the case over here. I'll start making the connections. But before that, I will suggest that you place all the components and then start wiring up the circuit. Okay, what is the next component that we are supposed to have? Next component is the LCD itself. Now LCD, again we can go on to Snap EDA and download the schematic symbol and the footprint also. So here we have 2x16 LCD. I'll be using that if it is available. Otherwise, we'll go for a different track. Okay, it seems to be available. So I'll download it again. The same process I'll continue. Copy it to my folder, project folder. Now I get rid of this, and again I have to install that library. So install from file, LCD, close. Now I'll be having the symbol for LCD as well. Place the LCD. I'll place it somewhere. Okay, I may have to make some changes in the layer, in the placement. So maybe let us get rid of this first. Place it here. Okay. Now for that other component like DS18B20, it's a 3-pin component, so I can use a connector over there. I need not actually get the footprint and all those things for that. Okay, so I can use a connector. Again, a header with 3 pins, and I'm going to call this as sensor, so S1. That is a temperature sensor. You may hide the details, these details, not really required. Get these details also I can hide. This, of course, is important. I'll call this as LCD. Okay. Now I can start wiring the circuit because almost all the components are there with us. Okay, so we'll start first of all with the ground. So here, connecting this to ground. Bring this to ground. We'll have multiple grounds here. Okay, let us wire this ground. All right. Then if you carefully see that these are multi-pins, multifunction pins. A5 is SCL and A4 is SDA. So correspondingly, I'll have to connect these pins A5 and A4. And just place it like this. Okay, then we require the pull-up resistors R2 and R3. I can rotate it again by 90 degrees here. This may not be required. It unnecessarily clutters the schematic. Okay, I can connect it here. I have to connect it here. All right. So this takes care of the CL and SDA. VCC I can connect here. Okay, I would require a crystal also that we have missed somehow. So let us get a crystal. So crystal over here. name it as X1. Do away with this. Okay, so that completes this part. For this, we'll require to consult where exactly we have connected the sensor. So it's a one wire sensor. You can see here it is connected to D10. So assuming that this one is VCC, this is the DQ output of the sensor. Now, if you don't know what is the DS1307, let us go back to DS18B20. Sorry, DS18B20. So it's actually, we'll see. Look at the circuit diagram. It's supposed to be connected to VCC, ground, and only one wire is required. And of course, you are required to have a pull-up resistor on that data line. So I'm going to use a pull-up resistor. That's all. The only thing that is remaining now is the connection with the LCD. So that again, this goes here. Let us have a look at the connection. This VEE is equal to PO. That also can be grounded. I'm going to keep it open. This is for contrast setting. Okay. Then we have RS connected to D12. So let us wire it up that way. RS is connected to D12. Okay. Then R read write bar is connected to ground. I have another ground here. Enable is connected to D11. Let's see this. Let me make this a little change. Then we have 4 different connections. Let me just modify this a little bit. Okay. Fine. So we start with D4. We connected to D5 of the device, D4 of the LCD to the D5 of the device. Then D5 of the LCD connected to D4 of the device. That's about it. So we have completed the wiring of the entire circuit. Let's have a look at it. All right. Hello. Hello. Am I audible?
Yes, sir, you are audible.
Okay. So what we are looking at is a completed schematic diagram of the circuit that we want to make the PCB of. Okay. Of course, there are some things which are still remaining. Like, no, that's okay. We have finished it. No problem. So that is it. Only one thing remaining, and that was the supply for the magnet. Please remember, it means that I'm not using the USB power, but I'm using a power which is given externally, like this. So that finishes the schematic. Let us save it. Okay. Let us quickly see whether each of the footprints of these schematics are available. So we already know the footprint for this is already there. You can see here. Footprint is already there. No problem with that. For this guy, footprint is already available. For this connector, also footprint is available. For this, footprint is available. This also we have a footprint which is available. For registers we have already seen. The only thing that is there is we don't have a footprint here for the device symbol that we have created. We don't have a footprint as yet. Okay, so we will start with how to create the footprint. I'm just going to